Under the discussion of angular momentum equation, now we turn to some special cases when the flow is steady, when the flow is different from steady motion, and when various forces are acting in a different situation. So we take into consideration and we consider some special cases with reference to that. One of them is a rotating lawn. To give you a practical example, in our lawns, we give them water, we provide water to the lawn by using sprinklers, and these sprinklers, they rotate. When they rotate, they sort of provide uniform distribution of water to all parts of the lawn within the range in which they are effective. So if there are several one of them, then they save water, they are economical and more effective as compared to watering through pipes and so on. So a rotating lawn sprinkler is a good example of application of the angular momentum equation. And for steady flow, the total angular momentum will be given by over a control system will be R cross V. R is the radial vector, the V is the velocity vector, times rho, the density, times VR dot n, the normal unit vector in the direction normal to the radius, the radial direction, times the area of cross section, dA. So an approximate form of the angular momentum equation in terms of average properties at inlets and outlets is equated by this equation, which is very much similar to the equation that we had in linear motion. There also we had similar terms, and here the same thing, except that the terms are substituted by taking into consideration the motion in the rotational direction. So we have total angular momentum forces equals to integral over the control volume and then differentiating it times summation at the outlet and minus at the inlet, so that the all forces on the whole system are considered and they are taken into account. If some of them turns out to be zero or simplified, then we substitute their values according to the situation. For example, when the flow is steady, then it will mean there is no change in the motion of the fluid with respect to time. Mathematically, that would imply d by dt is zero. So, therefore, this part d by dt of the, whether it is velocity or distance or other, where the flow is steady, there is no change with respect to time, and therefore this total component has to be zero, and so we have to remove that from the equation, and for steady flow this equation will be reduced to this form, and we can write it, of course, in this simplified form as well. The net torque acting on the control volume during steady flow is equal to the difference between the outgoing and the incoming angular momentum flow rates. So the net torque, which is reflected by this force, the summation of all the terms that may occur here, is equal to simply these terms, that is the angular momentum occurring at the outgoing flow and at the incoming angular momentum flow rates. So the difference will give us the net torque that is taking place on the system as a whole, on the control volume as a whole.